Diethelm is a professor of mathematics and applied computer science at the Technical University of Applied Sciences, Wurzburg-Schweinfurt, Germany, where he leads the scientific computing laboratory. He holds a diploma in mathematics from TU Brunswick and a PhD in computer science from the University of Heidelberg. His main research interests are approximation theory and its applications, analytical and numerical aspects of fractional calculus, especially fractional ordinary differential equations and high performance computing. We are very happy to host you, Professor. You may please begin your talk.
Yes, thank you very much, Pavan. Thanks for giving me the opportunity to present some of my recent results here and to give a certain impression of some specific aspects of fractional calculus and numerical fractional calculus in particular. So the title of my talk is Efficient Algorithms for Computing Fractional Integrals. Here's a little overview, first of all. So I'm going to begin by giving a little bit of a background. Why are we doing all of this? In the second stage, I will talk about diffusive representations. Diffusive representations are a special way of writing down fractional integral, in our case, fractional integral operators. And this slightly non-classical way of writing down those operators gives great opportunities for numerical work in the sense that it allows you to design numerical solution methods which are very, very efficient in various different respects simultaneously. And I'll go into details about that. So in the next section, I will then talk about what our numerical approach looks like based on such diffusive representations. We'll see that there are still certain weaknesses, so we're going to look at an improved approach. And finally, I'm going to give a very short outlook on what it means and what we can achieve when we apply such algorithms to solve fractional ordinary differential equations. The work that I'm going to present here is, for the most part, joint work with my group members, my team members, Renu Chaudhry and Afshin Farhadi. And also we've collaborated in this project with André Schmidt and Paul Haker from the Nonlinear Mechanics Institute at the University of Stuttgart. And all of this has happened within the framework of a project financially supported by the German Federal Ministry of Education and Research. Before I begin talking about fractional integrals and their numerical handling, I would like, however, to give you a little advertisement for an event which is coming up in the next spring. I've just heard that it's been approved and it's going to happen. So this is a so-called blended intensive program. A blended intensive program is a series of lectures supported by the within the framework of the Erasmus program. And it's called blended because it comprises two parts. In the first phase, we are going to, all participants are going to meet face-to-face in a certain place. And there, a handful of experts are going to give some lectures. And in the second phase, we have a virtual phase where the participants collaborate on projects over the internet. It's a program devoted to fractional models in engineering, as the title says. So we will have mathematicians in the group, electrical engineers, mechanical engineers, physicists, and control engineers. And they will all explain to the students, to the audience, their view of fractional calculus, why they think it's important, and how to apply it. So this is a program which is targeted at master's students, PhD students, and postdocs mainly, but other persons are also welcome as long as we have open space. The face-to-face part is going to be in February 2025 for 2 weeks, and it's going to take place in southern Italy, in Bari. And the virtual phase is then going to be in March and April next year. And the idea behind those blended intensive programs within the Erasmus framework is that students can collect credit points for such a module towards their master's degree, for example, or if the PhD program demands that, we can also make that happen. For the travel expenses, the participants can receive funding from the Erasmus program, at least as long as you are in an Erasmus partner country. So this is something that your international office can arrange for you, except for participants from Italy, which is the case because the face-to-face part takes place in Italy, and Erasmus does not support travel on a domestic level. So participants from Italy, I'm afraid, have to find other sources of funding. Yeah, so this is something that we've just heard, that it has been approved, that is going to happen. More details will be published soon. And if you have any questions on that, please feel free to contact me, and I'll try to answer everything that you might want to know. Okay, now back to the topic. So what's the background of what we're doing here? The background is that we want to solve an initial value problem. In the general case, something that looks like this here. It's a first simple special case. So we have some unknown function y, depending on the free variable t. And here we have the Caputo derivative of order alpha of that function. Alpha throughout my talk is going to be between 0 and 1. That's not really a necessary restriction, but it helps keep the formulas a bit simple and not too complicated. In fact, you can extend almost everything what I'm going to say here to arbitrary values of alpha, arbitrary positive values of alpha. But then many of the formulas become more complicated. But you can do that if you like. You all know that when you have such a differential equation here with the Caputo operator, and alpha is between 0 and 1, well, you have to expect to have infinitely many solutions. And in order to get uniqueness, you would usually combine the differential equation with such an initial condition here. So 0 is, in my case, always the initial point, the point where the differential operator or the associated integral operator has its lower terminus. And this is just the standard definition of the Caputo differential operator. Yeah, so under the standard assumptions that little f is a continuous function and it's Lipschitz with respect to its second variable, then you know that this has a unique solution. And we assume that the solution exists on some interval from 0 up to a point t max. This is something which arises in a number of applications, and what we have in mind here in our project is a very specific application. That is, we're doing something in mechanics. We're simulating the behavior of a viscoelastic body, a body made of some viscoelastic material under an external load. And classical laws of mechanics then tell you that you can formulate the relationships between stress and strain in the form of such a differential equation. And when you want to model things like this, well, what an engineer typically does is they apply a finite element method. So that means you take your body, you divide it up into lots of very, very many small finite elements, and then you solve things on the elements. And on each Gauss point of the finite element scheme, you then have one of those differential equations. And that means we're not talking about having to solve one differential equation. We are talking about a huge number of differential equations, all of them having a form like this here. So we can often encounter a couple of millions of such differential equations. And we have to solve them at the same time. You could call this a system of differential equations. I prefer not to, because the notion of a system implies the tacit assumption that there is some kind of interdependence between all those equations. And that's what we don't have here. So we have lots of totally decoupled differential equations. There is no interrelation between all of them. So you can, in principle, solve every single one of those equations on its own without having to take into account any of the other equations. So that makes life a bit simpler. What makes life very much not simple is that the differential operators, as you probably all know, are not local. And that induces major challenges in two respects. First of all, runtime, and because you have to take into account the history, the memory of the process, and you have to store all of that in your computer's RAM. So you also have to make sure that you don't run out of memory. Runtime actually is an issue that has been addressed in the past quite frequently. Memory has not so much been in the focus, but when you talk about millions of such equations, then you must take into account memory as well. Okay, the fundamental approach that is very common in such applications is that you rewrite the initial value problem in the form of a Volterra integral equation with a Riemann-Liouville integral operator. And you can prove that this is equivalent in the sense that if you find a solution for the Volterra integral equation, you also find a solution for the initial value problem. So when you can find a numerical solution method for this integral equation, you're done. And the essential ingredient in all those solvers is an algorithm which allows you to numerically compute such Riemann-Liouville integrals. For some given function z, you compute the Riemann-Liouville integral of order alpha of z at your points of your time discretization, at the points t little n, where little n goes from 1 up to capital N. So that's what we're trying to do here. And we're trying to do that in a very specific way. We have some goals that we want to achieve in that construction. The first one is the computational effort. We want the total computational effort to be of order capital N, not more than that. So as many operations, the number of operations should be proportional to the number of time steps that you're taking. And also, we want to do that with an efficient memory management. And that means we want to have an active memory requirement, which is capital O of 1, which is constant. No matter how many time steps we want to take, we don't want the amount of memory that's required to increase. And of course, that's also absolutely essential. We need to keep the error under control. So basically, those goals are exactly those that you would naturally expect to be achievable in the case of a first-order differential equation, which, of course, is an equation without any memory. And that's what we want to get here as well. Okay, so once again, these are our errors. And how far can you get with classical methods? Classical methods, for example, include the fractional multi-step methods that Lubich proposed already about 40 years ago, or our predictor-corrector methods. And you can implement those methods in a straightforward way, in the way that they are written down and described in those early papers. And when you do that, you'll notice that the computational effort is not proportional to n. It's proportional to n squared. So it takes much longer. And the active memory requirement is also capital O of n. So that's too big as well. What we do have on the positive side is we have a very good understanding of the error. We have a very good error analysis, and we know pretty exactly what the error is. What you can then do is you can take those methods, multi-step methods, predictor-corrector methods, and implement them in a slightly more clever way, based on fast Fourier techniques. That has already been described by Lubich, Heyra, Schlichter in the 1980s. And Roberto Garappa picked that up about 15 years ago and implemented that in MATLAB in an extremely well-designed way. And what you get then is you can reduce the computational effort, not exactly up to capital O of n. You are still a little bit worse, but only a little bit. And most people would say, okay, we can live with that. The problem is on the memory side. On the memory side, you're stuck with the same nasty behavior. You don't get any improvement at all. And of course, as far as the error analysis is concerned, well, it's from a mathematical point of view, it's exactly the same formulas as before. They are only evaluated in a slightly better way, more efficient way, but the final results are exactly the same, so the error analysis is also the same. What can you do about the memory? Well, you can talk about things like nested meshes and related aspects. And when you use nested meshes, you get a computational effort, which is, once again, almost, not exactly, but almost O of n. So that's acceptable. And you can also cut down the active memory requirement to log n, which still can be too big. But of course, it's much better than n. And we have an error analysis, which is, well, a little bit incomplete, but for the most part, also pretty well understood. Okay, so we've got that. And that's why we now look for a completely different method, a method which actually achieves all those goals up here. And one way to get there is via so-called diffusive representations. Diffusive representations are in principle a well-known thing in fractional calculus, but I think the opportunities that they offer are often underestimated. And there are many ways to derive those representations. One of them, the one that I'd like to show you here, is based on a formula involving Laplace transforms. So consider this function here, t to the power of alpha minus 1. You can look that up in tables of Laplace transforms or things like that. You can see that this is the Laplace transform of the power, the negative power with negative exponent with exponent minus alpha, multiplied by some constant. So this is the full formula here. You take p to the power of minus alpha, put that into the Laplace transform operator, multiply by this constant, and you get t to the power of alpha minus 1. Now, why is that interesting? What's the significance of this? The reason is because this function here on the left-hand side is the kernel of a Riemann-Liouville integral operator. So the Riemann-Liouville integral operator is something that you can understand as the Laplace convolution of the function that you are integrating with this kernel function. Okay, but we're not going to stop here at this Laplace transform. We're going to do one more little analytical multiplication in the integral over here. Namely, we're going to introduce a substitution of variables. So our substitution reads that p is replaced by psi of omega. And psi is what I call an admissible transformation. An admissible transformation is a function with three very, very simple properties, and those are not very restrictive. This definition gives you a huge amount of freedom in choosing that transformation psi. So first of all, psi should be defined on some domain capital omega, and omega is supposed to be an open interval on the real line. And psi maps into the positive numbers, into the open interval from 0 to infinity. Psi should be C1. It's supposed to have one continuous derivative on its domain, and it's supposed to be strictly increasing and bijective. And if you plug that in, you get this formula here. So t to the power of alpha minus 1 is this constant times the integral, which now ranges over capital omega. And what you get is this here. E to the power of minus psi of omega t, psi of omega to the power of minus alpha, psi prime of omega d omega. Okay, so we take this and we plug that into the definition of the Riemann-Liouville operator. So we replace the kernel by this expression. And when you get that, when you do that, you arrive at a representation that looks like this. And this is the so-called diffusive representation of the Riemann-Liouville integral of the function z. So the Riemann-Liouville integral of order alpha of the function z can be written in this way here. Integral over the set capital omega, the interval capital omega, of some function phi tilde, which is now a function of two variables, t, the free variable here, and the integration variable little omega, over which we integrate. And this function phi tilde, known as the infinite states, can be written in this way. It's c alpha of omega times phi of t comma omega, where c alpha is this here, sine pi alpha over pi, and then you get something which contains the admissible transformation. And of course, we're talking here about something which depends on the given function z. and the dependency on z is hidden here in the function phi. So phi is this convolution integral here. Integral from 0 up to t, e to the power of minus psi of omega, t minus tau, z of tau d tau. So that depends on the given function z, on the function that we want to integrate, although I haven't mentioned that explicitly. Some examples. The classical one, psi of omega is just omega, already introduced 25 years ago, 26 years ago. Others introduced in the context of numerical methods are omega squared or omega to the power of 1 minus alpha. And all of these lead to capital omega being the positive numbers. You can also work with exponentials. So you can say psi of omega is e to the power of omega, or exponential function of omega minus e to the power of minus omega. And then capital omega is the entire real line. And you can also think of functions psi where omega becomes a finite interval. For example, the tangent here, or this sigmoidal transformation. Now, how does that help us in numerical work? Well, first of all, we have to find out some of the essential properties of the integrand here in this representation of the kernel. And we can see that the integrand has a certain asymptotic behavior as omega tends to the left endpoint of the capital omega. And also we can find an upper bound as omega tends to the right endpoint. And we can also see that it's k minus 1 times differentiable if psi is k times differentiable. So that tells us a lot about the differentiability properties and the asymptotics of the integrand. And from what you know from numerical integration, those are the crucial points when you want to approximate such an integral numerically. So what we can do is we can introduce a weight function, w, that matches the asymptotic behavior. And then we interpret this integral as a weighted integral with respect to this weight function. And we select a quadrature formula that corresponds to this weight function. So we get this formula like this, a sum of a weighted sum of function values of the integrand. And when you apply this formula to this integral up here, you get an approximation of this power function, which essentially contains lots of constants here. All these are constants. And here you have exponential functions. So this is a so-called sum-of-exponentials approximation of the power function. And then you plug this into the kernel, into the representation of the kernel for the Riemann-Liouville integral. And you get a representation, an approximate representation for the Riemann-Liouville integral in this form. So this is also a weighted sum of function values of our function phi that we had seen earlier. The rows here are negative numbers. So those are the points at which we have to evaluate the integrand function. And it's going to be important later that those numbers are negative. The a kappas are some constants, not so relevant at the moment. The crucial point is what this function phi here is. Phi is this convolution integral where one factor is an exponential and the other factor is our function z. And because of the very nice analytical properties of the exponential here, you can differentiate this with respect to t and see that this function satisfies this differential equation. And this is a differential equation of order 1, not a fractional differential equation. This is integer order. And you get an initial condition here. And in fact, when you look at this differential equation a bit closer, you see it also has some extremely nice properties. For example, it's linear. Our unknown function is phi. It's inhomogeneous. Here's the inhomogeneity. And it has constant coefficients. Rho is just the coefficient here. Remember, this is differentiation with respect to t, not rho. So rho is a constant. So that's very nice and easy to solve. On the other hand, we have to evaluate that when rho is one of these guys here, which are less than 0 and which can be very, very much less than 0. And that means we're talking about an equation that can be extremely stiff. Okay, but we've already got our first component for our numerical method in place. And the second component then is we need to solve this initial value problem, and we can do that with a standard solver, taking into consideration the properties that we've just found out. So in particular, this gives us a complete freedom regarding the choice of the grid points in our time discretization, but the ODE is very stiff. So when you solve that numerically, you should use at least an A-stable solver. An L-stable solver is even preferable. So you could try backward Euler or an exponential integrator. And when you implement that, you can see what the computational cost is. The total operation count is of the order of k times n. K is the number of nodes in your quadrature formula, and n is the number of time steps. And the active memory requirement is of the order k. And the basic idea behind of all this is that k is a fixed constant. So by construction, you automatically get those two crucial features that we want to have for the efficiency. On the other hand, the error analysis of all of this is going to be pretty challenging because we have multiple components that influence each other. We have the ODE solver and we have the quadrature formula. So what is a suitable admissible transformation? For example, what was suggested first in the literature was those power functions here with certain positive exponents. And what you get then is an asymptotic behavior of the function phi, that's the integrand, which exhibits algebraic behavior. And algebraic behavior as omega tends to 0 is no problem. You can take care of that with a suitably chosen weight function in your integration. But algebraic decay as omega tends to infinity is not so nice. Is something which means, by what we know from numerical integration over unbounded intervals, that's difficult to approximate with traditional methods, at least if you're interested in something that converges rapidly. This just decays too slowly. So the alternative suggestion that we now look at is when psi is the exponential. In that case, capital omega is the entire real line. And then you notice that you get an asymptotic behavior, which looks like this. You get an exponential decay when omega tends to infinity, and you also get an exponential decay when omega tends to minus infinity. So that decays much faster, and that means you can apply traditional quadrature methods. You can apply them successfully. So this is our numerical approach here. In summary, we know that this is difficult to approximate. Oops, we've just had that slide. So our numerical approach looks like this. We choose some mesh points on the time discretization. We use a diffusive representation where psi is the exponential, and we define a quadrature formula over this real line here. We split that up into the negative half line and the positive one. On each of those, we plug in a linear transformation, which gives us an integrand behavior behaving as e to the power of minus absolute value of omega. when the absolute value of omega becomes large. And then we use a Gauss-Laguerre quadrature method on each half line with k over 2 points. So altogether we get k quadrature points. And then we can use a backward Euler method to solve the initial value problem for the quadrature nodes. So we have one of those initial value problems for each set, for each of the quadrature nodes. So we have k of those initial value problems altogether. And then we can use put all of that together and approximately compute the fractional integral by the basic formula here. What you can get, for example, is an error estimate like this. When your function is twice differentiable, and that's a very restrictive assumption. So that's something that you normally don't have in fractional differential equations. But if you have that, you can see that the error is bounded from above by something which is of the order k, number of quadrature points, to the power of minus p, where p can be an arbitrary positive number. So this is very small when k is large, when you use many quadrature points. But then you get a second component, which is this here, h squared plus e to some power of some constant, or depending on alpha, times k. So this here is big when k is large. And if you want to get that whole thing small, you have to compensate for that by making the step size here, the time step size, very small. Here are some examples. I'm trying to approximate the Mittag-Leffler function, E alpha minus t to the power of alpha over the interval from 0 to 1. I've done that here with 20 quadrature nodes, step size 1 over 80, and alpha is 0.4. What you can see here is the approximation errors for 3 different variants of the ODE solver. In blue, an exponential integrator, which you can see gives a very small error here and a very nice regular behavior. In red, that's backward Euler, which is similar. In green, it's a trapezoidal method, and that looks somewhat different. There's massive oscillations here. The numerical solution oscillates around the exact solution. And the reason for that, I'll say something about in a few minutes. When we change alpha to 0.6, we get a very similar picture once again. So you get all those oscillations for the trapezoidal method, but not for backward Euler or like the exponential integrator. And what you can also see is those oscillations have a relatively large amplitude here at the beginning, and the amplitude becomes smaller, so that dampens out. And the origin of those oscillations, well, they have been investigated. The origin is that the trapezoidal rule, which shows all those oscillations, is not L-stable, whereas the backward Euler is L-stable. So when you solve a very stiff differential equation with a trapezoidal method, you expect to see such oscillations. Here's a different example. Z is now a power function. And now I've not plotted the error over that interval, but I've plotted the maximum error over the number of grid points with a uniform step size. And I've done that for various different numbers of quadrature nodes. And you can see larger number of quadrature nodes means smaller error. And when you decrease, or when you increase this number of steps, when you decrease the step size, you also get a smaller error. But there is some kind of a saturation. At some point here, decreasing the step size does not provide any further improvement. and that's because your error has multiple components, one coming from the numerical integration, and when you just change the step size in the ODE solver, you don't change the numerical integration, you don't change the error of that, and over here, this is the dominating part. When we compare that with a classical method, like an Adams-Bashforth-Moulton with the same step size, you can see the errors are much smaller. So what we can see is we can obtain equality with our methods, which are comparable to classical ABM. But to do that, you need a numerical integration with very many nodes. And that means the whole thing is not going to be as fast as we want it to be, and it is not as memory efficient as we want it to be. So what is the background of this not so satisfactory behavior? Let's just go back to this representation of the Riemann-Liouville integral. And yeah, well, we've got this kernel function, which can be written as the Laplace transform of the power function. And we introduced our substitution. That's what we did a while ago, a few minutes ago. And then we replaced the integral by a numerical quadrature formula. And we can plug this one in here now for the kernel function. And what you get is an expression that looks like this. So this is more or less the same formulas except for the normalization that we've had a few minutes ago. And once again, we have this linear first order initial value problem. So this is up to the normalization. This is the same as our earlier scheme. So what we can learn from that is the essential point in our approach is that we replace the kernel function, this one, t to the power of alpha minus 1, by this approximation, by the sum of exponentials. And in our case, alpha is between 0 and 1. So that means the kernel function here is an unbounded function near 0. But we're trying to approximate this unbounded function by this one here, which is a sum of exponentials. So this is bounded. So we're trying to approximate something which is very large, at least in some regions, by something which is not large. We need an approximation here in L1 sense. So that's something that you can do, but of course you can do better. So let's improve the approach. And the basic idea is you decompose the Riemann-Liouville operator. You split it up into what's called a history part and a local part. So in the Riemann-Liouville integral, you integrate from 0 up to current time point Tn. And you split that up. You take away the last subinterval, that's your local part, and everything else is the history part. And in the local part, you don't go back in the process history. So you have no contribution from the process history, which means you can use standard methods to approximate that accurately in O of 1 time with O of 1 memory. And in the history part, well, now you have no singularity in the kernel function anymore. The singularity is when tau is equal to Tn. But we end the integration here at Tn minus 1. Everything that's behind Tn minus 1 is up here, but not down here. So there's no singularity in the kernel function. And therefore, we can use our techniques, our earlier techniques, and we don't run into this bounded versus unbounded problem anymore. So once again, with those techniques, you can also compute this one accurately in O of 1 time with O of 1 memory. For the local part, you can, for example, use a weighted trapezoidal quadrature formula. Or if you prefer, the fractional Adams-Moulton method. which is very well understood, well investigated. You can find out something about the error under various assumptions on the given function z, and so on. For the history part, well, you can proceed much in the same way as before. It's now going to be everything formally a little bit more complicated because you only integrate up to t minus h and not up to t. But that's not a big deal. It means that you once again get a first-order initial value problem, which looks a bit more complicated here for this diffusive representation for the infinite states. But it's, yes, well, it's only formally a bit more complicated. And if you set h here, the step size to be 0, you arrive again at the form at the previous formulas. So from now on, we shall assume that we are talking about a uniform discretization in the time interval. It makes the formulas a little bit simpler. So once again, we can find out the essential properties of the integrand in our diffusive representation. We can get k minus 1 times differentiability if the admissible transformation is in ck. We get C infinity if the admissible transformation is in C infinity. And we can find the asymptotic behavior as omega tends to the left and omega tends to the right endpoint of the integration interval. So this is all we need to know about integrating, to find a suitable integration method. And furthermore, if z is L times differentiable, then we can also see that this this function here, this infinite state function, is in CL plus 1 with respect to the time variable. So that means, from approximation theory point of view, the function mu in the integrand of the history part, the infinite states really, is at least as nice as the infinite states in the classical representation. And in fact, in some cases, it's even better. So we may expect better results. And what we get indeed is something which converges a little bit faster, but not all that much. Why is that the case? Well, the reason is probably the numerical integration method. Gauss-Laguerre assumes the integrand behaves with a certain speed, decays with a certain speed. And in reality, what we have here in our estimates is just an upper bound. So we have reason to believe that in reality, the integrand decays faster. And that means the Gauss-Laguerre quadrature method overestimates the value of the integral. And there are ways to resolve that. We need to investigate that in more detail in the future. But what we can do, first thing is we can use a different integrator. So we can, for example, truncate the integral at suitable finite points and use, for example, a trapezoidal method for the remaining finite integral. Truncation makes sense when the integrand decays so fast that everything beyond the truncation point doesn't contribute in a meaningful way anyway. Another option would be to use a different admissible transformation because the admissible transformation essentially determines the asymptotic behavior of the integrand. So one thing that you can use and that looks pretty promising is this one, which was suggested by MacLean, and that gives an even faster decay and allows you to truncate the integration even earlier. Or maybe you can use other integration techniques altogether. So as far as the truncation of the interval is concerned, here's something that we can show. So once again, we're looking at the integration of the Mittag-Leffler function. over the interval from 0 to 10 with a step size of 0.1. And so the idea is, instead of integrating over the entire real line, our set capital omega, we know that the integrand decays fast, so we can truncate that. And if we want to truncate that so that the error of the truncation is less than epsilon, we get results like this here. When we have an order alpha of 0.4, and we want an or epsilon of, say, 10 to the power of -6, instead of integrating from -infinity to infinity, it's enough to integrate from -25.8 to plus 5.1. So that's something that can significantly simplify things. When alpha gets bigger, you need a somewhat larger interval, at least on the negative side. On the positive side, it doesn't make much of a difference. So that's a plain and simple exponential. When you use MacLean's suggestion, you can get along with a much, much smaller interval. So once again, on the positive side, the truncation point remains almost exactly the same. But on the negative side, you can improve a lot. So instead of the -25.8, you can use -3.2 here, for example. And something similar happens when alpha is 0.7. So using MacLean's transformation allows you to truncate the integral much earlier, at least on the negative semi-axis. On the positive semi-axis, there's very little difference between the two transformations. And then the remaining integral can be approximated, for example, with a trapezoidal method with a certain mesh size, and you have to determine that mesh size, of course, so that it matches the desired accuracy level of which you introduce by the truncation. So it doesn't make sense to truncate at a point where you get a very, very small error, and then you use a very big step size so that you get your big error through the back door. Finally, let's take a look at the application to some specific fractional ODE. And I'm going to look at just one single equation system here, which is something that my PhD student Safura Hashemi-Sharaki came up with, this suggestion. So this is a system of differential equations. And it's a little bit more challenging in the sense that we have 3 differential equations, and each of them has its own order. They don't have all the same orders. For many numerical methods, this can be quite a challenge. For our approach here, this is absolutely no problem at all. You can very easily apply the method for systems like this as well. The system itself is linear and inhomogeneous. And there are some analytical methods that we've developed recently. And using these analytical methods, we can show that the system is asymptotically stable. So that means and these y's should be x's and not y's here. Sorry. That means that the limit of the solution vector is 0 as t tends to infinity, no matter how you choose the initial values. And here's the image that we get when we apply our method to this system. So what I've plotted here are 3 curves. And so this is an algorithm that was then implemented by Afshin Farhadi and also analyzed by my colleague Renu Chaudhry. So we have 3 curves here corresponding to the 3 components of the system. And we've done that with the Gauss-Laguerre method, 50 nodes on each semi-axis. And for the ODEs, we've used the backward Euler solver with a step size of 0.1. And we've used the simple exponential as the admissible transform. To check whether our results were correct, we've also solved the system with Carapace implementation of the classical fractional backward Euler method with the same step size, and what we got was this. So this doesn't look like this here. I've plotted that on the interval from 0 to 1,000. So something seems to be wrong here. To see what happened was then we decided to reduce the step size here in the Carapace method. And when you do that, get to 1/18 instead of 1/10, you get this. And that is very, very much the same as what we had in our method. So we are somewhat reasonably confident that our results are not too bad. Now let me just show you one more visualization here. So here's, we're talking about a three-dimensional system, so you can interpret the solution components as trajectories in three-dimensional space, and this is how the solution behaves over time. And you can see something looking very nice and, going around the origin and converging to the origin eventually. So if I were to run this for another minute or so, you would see that the whole thing gets closer and closer to the origin. And so that's what you get here. Good. Now, so this is what we get with Carapace method, and what can we learn from that? Well, we can still try to play around a little bit with the step size, and that's what I've done here. This is our method, and now I've plotted only the first component of the solution, only x1. With various different step sizes. And you can see there's some kind of a pattern here. You get those oscillations, damped oscillations. Notice, please, that we have a logarithmic scale on the horizontal axis. And what we can see is decaying oscillations. And when we decrease the step size, so we increase the number of steps, we move from here to here to here to here to here. So when you look at the local extrema, they remain at the same abscissa, no matter what the step size is, but the ordinates get bigger. And when you look at the other components, x2 and x3, you get pretty much the same result. So here what I've done is I've gone up to 10,000 time steps. So that's the step size of 1/10. And then I made the step size even smaller. So for 10,000 step sizes, I got this behavior, 10,000 steps. For 10,300, I got this one, still going down to 0 here. But for 10,600, the behavior completely changes. It blows up. And that's no more asymptotically stable. But we know from our analytical results, it must be asymptotically stable. The reason is probably, I'm not sure yet, the given system here is stable, asymptotically stable, but it's pretty close to an unstable system. If you change it a tiny little bit, it becomes unstable. So when you take too many steps, the rounding errors may accumulate to an extent that brings you out of the stable regime into the unstable regime. Now you may say that's a very weird behavior and you shouldn't have that in your numerical algorithm. So let's see what other algorithms do. And let's take a look at Garappa's fractional Euler method, fractional backward Euler, which is really the gold standard of numerical methods in terms of stability. So what you get here, when you increase the number of time steps, when you decrease the step size, you get a picture which looks very much the same. You get all those oscillations, the extrema remain at the same abscissa and get bigger ordinates. And then you increase that even more, and what you get is exactly the same behavior. I found that quite interesting because those two numerical methods are constructed according to totally different ideas and principles, but in this respect, they behave in very, very much the same way. Okay, so let me finish with some open questions. First of all, what is a particularly efficient combination of quadrature formula on the one hand and admissible transformation on the other hand? And then there's the other component of the solution method, the mesh with respect to the time interval. So what is the particularly efficient combination of the number of quadrature points and the mesh? And what also plays a role here, if you truncate the integration interval, the truncation point. And, well, can we derive explicit error bounds, not just asymptotic, but explicit? And how can we prove the stability of this approach? Stability is an essential point in any numerical method. And for methods based on classical design principles, we have ways to prove that ever since Lübich's pioneering work 40 years ago. How do you do that with a formula based on a diffusive representation? We don't really know that yet. There are some steps in that direction recently, but the knowledge is far from complete. And finally, what is the reason for the observed behavior in the last example as the step size is decreased? Yeah, so that concludes my talk. Thank you very much for your attention. And I've already seen there was one or two questions in the chat. So let me just, yeah, there was, no, it has disappeared here somewhere. Okay, but I think there was a question in the chat, which for some reason I can't see right now anymore.
Yeah, there was. I'm not able to see it as well. Probably it was deleted by the user itself. But anyway, if there is a question, please ask. Please raise your hand. This was a very nice talk, I have to mention, and please raise your hand, so I'll call out your name as they appear on my screen. All right, I don't really quite see raised hand, but I have to mention it was actually very much interesting for me, and the questions you raised were of a very practical nature. So I have a couple of questions. So let me understand this. So you have this diffusion represent. You have this quadrature formula, which is basically the sum of the coefficients and the function phi, and the function phi you evaluate by using the you have an ODE expression and ODE expression for phi, and then you plug back in that quadrature and quadrature, but that gives you the kernel, right? Doesn't give you the hold on. Can you go
yes,
back?
That's right. Yes. That's right.
So, okay, this gives me the kernel or the value of the fractional integral. Okay, this gives me the...
no, this, well, if you can look at it from either way, whatever you prefer. You can use the quadrature formula to approximate the kernel. And then you plug this approximation for the kernel into the representation of the Riemann-Liouville integral. And then you simplify all the resulting expressions, and then you get an approximation for the Riemann-Liouville integral. So you can look at it from either way, whatever you prefer.
Okay. 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 And this omega k, which is an argument for xi, that range is dependent upon what is the function xi.
Well, omega k, the little omegas are the quadrature node points. So those are the points where your quadrature formula evaluates the integrand.
Fair enough. Fair enough. So you had some couple of choices you mentioned, like truncated in domains and things like that. So so that would be very much dependent upon what is the domain. Hold on a sec. That
Yes, and
something is not quite adding up.
and
Please.
that in turn depends on what your transformation psi, or what kind of transformation psi you choose.
I see. I see. I see. So the original domain can be 0 to t, but the transformed domain can be anything.
It has to be an interval, but it can be any interval really, depending on how you want to choose that that function psi.
I see. I see. In terms of error analysis, basically you have some function, let's say u to be approximated. You have u minus the quadrature uq plus the other term, which is uq minus the ODE error, and then you bound the ODE error plus the other. So basically there are two terms in here to be bounded.
Yes.
And one is coming from classical ODE solver, and the other error is coming from the choice of the quadrature.
Exactly. Yes. Yes.
Okay, so in some of these choices of the ODE solver, you used Euler scheme. Have you tried with Range-Kutta or looked into it?
No, we haven't tried that. Mainly because, well, we really need something which is A-stable, or even better, L-stable. And that limits your opportunities, your options when you want to use Runge-Kutta.
All right, all right, all right. In the other improved approach, you had a history term and plus the local term. So for the history term, all right, for I know all the values, so I know all the values, so I can compute that integral exactly. But in terms of memory, I would rather choose a diffusive representation, but then that diffusive representation will give me an ODE, and hence the error from which ODE I will be using. So now this is a bit of a trade-off. If I directly use a quadrature formula, the errors will be nice, but then I need to store everything, memory.
Yes.
But with the diffusive representation, would I still not need to store everything? I'm thinking.
If you use a diffusive representation here for the history part, you would still be memory efficient in the sense that you don't need to store the entire history. You just need to store one time level, the data from one time level back, but not back to the very beginning.
Okay. 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 So that's a efficient implementation, but you still have some numerical errors that needs to be worked upon. All right. Right. That's pretty much all on my side. If I have further questions, I'll probably reach out to you at some point. Meanwhile, does anybody from the audience have any questions, comments, feedback? Please unmute yourself and go for it.
Hi, are you able to hear me?
Yes, we can.
Yes.
Oh, okay, yeah. So I had a question regarding the your choice of the function e omega in your first case, or even in the
Mm-hmm.
improved. I think it might have been a different, slightly different. So were you able to try the methods with a more sort of the more complete Fourier, sort of like e I omega, or in the second case, or once you tried, like in your first case, I guess you didn't see the need for that.
For the admissible transformation, you mean?
Yes.
Well, the admissible transformation has to satisfy a number of properties down here. Those three properties. So in particular, it has to be a function defined on some interval and maps into the positive real numbers. And it has to be strictly increasing. So something like e to the power of I omega doesn't fall into that category. That's just not admissible.
I see. Yeah, I see. Yeah. Okay, thanks. Yeah.
Does anybody have any further questions? Probably no. So I'll close this meeting here. It was very nice of you, Professor Diethelm, to kindly come for this nice lecture on a very important topic. And indeed, it is correct that we have to memory versus computations, and we have to keep our errors low meanwhile. So that was very nice of you to think on those lines. Thank you very much for the nice talk.
Thank you. It was a pleasure.
Yeah. All right. We close the talk here.